Dr. Ni Hao from Oxford to present the work A Feature Set for Streams and a Demonstration on High-Frequency Financial Data. Ms. Hao will have 20 minutes. Okay.
Very much for giving me an opportunity to present my paper, A Feature Set for Strings and an Application to High-Frequency Tick Data. This is the joint work with my supervisor, Lyons, and my colleague, Harald Oberhauser. So in this paper, we aim to identify the functional relationship between the input and the output by learning from a large number of samples, where the input data is a string. So a string data is actually a sequentially ordered events. Which are observed at a sequence of discrete time points. And when the observation frequency are very high, it's important to summarize the string data. And in this paper, we proposed a new feature set for the string data, so-called the signatures of the strings, which can summarize the string data in terms of its effect, and it can be used to predict the output, combining with the regression techniques. So let me start with give the formal definition of the signature of the string. So the string S of x of bounded variation x is nothing else but a sequence of iterated integral of x. It seems very complicated, but actually for dimension 1 case, the signature of x can be reduced to the monomials of the increment times over n factorial. And for higher dimension, actually there is a almost a one-to-one correspondence between the underlying path x and its signature. So from the one-dimension case, we actually can think the signature of the path as a non-commutative monomial of the path space. So I would like to give a simple illustrative example to explain why the signature is a natural object for us to consider. So if we think about the linear differential equation, the yt is a solution to the linear differential equation driven by dyt equals to ayt dxt, where a is a linear functional, given the certain initial condition of y0. By Picard iteration, yt can be represented as the linear combination of the iterated integral of x. This factor actually says that if we want to know the output yt, we don't need to know the each point of x from time 0 to t. The only thing we need to know is the sequence of iterated integrals of the driving path x, and which is sufficient for us to give the exact solution of yt. Also, here I want to emphasize that it's important to consider the sequence of iterated integrals of x, the signature of x as a single object, because it has very nice algebraic properties and also analytic properties. One important property of signatures is called a shuffle product property of signatures, which is essential in our regression setting. So that is, suppose that we have two linear functional of the signatures, say f and f hat. Then there exists another linear functional denoted by f shuffle f hat, such that for each signature s, f of s times f hat of s equals to f shuffle f hat of s. This shuffle property is simply saying that any polynomial of the signature can be rewritten as a linear combination of the signature. So now we are in the position to give the general model. Suppose that under the probability space, sigma f is the filtration and p is the probability, and xt is e-valued stochastic process, and yt is another w-valued stochastic process. We assume that there exists a linear functional f hat such that the signature of y can be well approximated by the linear functional of the signature of x plus some noise. Well, the noise epsilon should satisfy the conditional mean of the epsilon given on the information x from time 0 to t should equals to 0. And our goal is to recover the linear functional relationship f by using a large number of samples, data pairs xi and yi. And so that actually, if we have the estimator for f, we can have an estimation for the conditional expected signature of y given on the signature of x. This is, roughly speaking, gave a complete description of the conditional law of y given on the information x up to time t. So now I want to, this model actually includes a large number of dynamic systems. An example is still yt satisfies the controlled differential equation driven by x, but here not only the linear controlled differential equation, but also if the vector field f is a polynomial by Picard iteration, the output yt still can be well approximated by the linear combination of the signature of x. And this is a deterministic case for our signature framework models. And another thing I want to emphasize here, the shuffle product property guarantees that the regression problem can be reduced to the linear regression problem by transforming the input data to the signature of the data itself. So I want to add some remarks here. If we think about the polynomial regression, we have the output y equals to f of x, where f is smooth. The polynomial regression is just we regress y against the monomial of x up to a certain level. Because f can be, by Taylor expansion, f can be well approximated by the polynomial. So do the linear regression of y against the monomial of x, we will get a pretty good approximation for f. In our case, it's pretty similar. So the input data is more complicated, but we transform the input data x, the entire trajectory of x from time 0 to t to its signature. That is the monomial of the path. And we regress the y against the signature. And the shuffle property of the signature guarantees that the linear regression will work if the output can be retained as a smooth function of the signature plus a certain noise. So, this idea is also similar to the kernel methods, because in kernel methods, actually, we use the kernel function to transform the underlying data to its future, so that after the transformation, we linearize the functional relationship between the output and the transformed data. But here we simply we use the signature as a particular feature of the input data string, and we do the regression of the output y against the signature of x. But the difference here is usually the kernel method is parametric. We should have some we should choose the kernel function based on certain knowledge of the understanding of the data itself. But in our framework, it's non-parametric. It's more robust. So now I like to add some more words about how to transform the signatures of the input stream data. As I mentioned before, if the underlying path is one-dimensional, the signature is nothing else but just record the increment information. So before transforming the path to its signature, actually sometimes we need to lift the input stream data to higher dimensional data associated to the underlying data. There are three popular ways to do that. The first one is a lead lag path. That is, we have one univariant time series. We shift it by lag 1 and add it into the original path, so that we have two-dimensional paths. And the signature of this two-dimensional path can determine the original univariant time series itself. Then we transform this two-dimensional path to its signature. And the second way is we add a time component to the original path, and then then compute the signatures. The third one is to accommodate it to the particular cases. Sometimes we need to normalize the path itself and then compute the signatures. The general procedure are summarized here. It's quite straightforward. So for each sample path x, we compute the truncated signature up to order n, denoted by Sn of x. So in the learning set, we do the linear regression yt against the truncated signature. We can use ordinary least square or more advanced techniques. Then after the fitting, we will get the estimator for linear functional f hat. Then we can compute the residues. It's simply the difference between the real output and the f hat act or the signature of x up to degree m. Then we check the goodness of fitting for both the training set and the backtesting set. So now we want to apply our method to real financial data. So the input data here is we fix a trading interval length, and we observe the high frequency stock price processes, and the output is a P&L of certain fixed unknown trading strategy. Our goal is to predict to the P&L for any given stock price processes. So for the trading strategy we use, we have two constraints. So here, actually the market is only consisted with two assets, one risky asset and one riskless asset. And for simplicity, we consider zero interest rate, no transaction cost. And the trading strategy, we assume it's self-financing. That is no rich uncle helping out. And the second constraint is that the trading strategy is an adapted process. That means that the trading strategy, the trading decision, trading strategy only depends on the past information of the stock price. So the example we are looking at is the high frequency tick data of IBM shares. And the unknown trading strategy here, we use the Kelly strategy. That is, we always invest a fixed portion of the current wealth to the risky asset and rebalance our portfolio accordingly based on the self-financing constraint. And we have the samples of the P&L and the stock price. We do the regression against different explanatory variables. So the first one is the price increments over the subinterval, and the second is the price increment and the variance of the price during the trading interval. So the price increment and the variance are two nature feature of the in finance, and the third one is the truncated signature of the price processes. So we will use the first and the second regression as a benchmark to compare with our regression results. And because I don't think I have enough time, so just show the plots. For all the learning set and the backtesting set, our methods outperform the other two methods, and I summarized the statistics of those regression methods into this table, and we can see that as the signature level is going higher and higher, the R square is improving, and in terms of the future work, we actually we will there actually have some overfitting issues about our work. So when the degree of the truncated signature is too high, the overfitting occurs, and we can consider to use lasso to handle this problem. And the second direction of our work is that we might think about how the regression results will be if we change the basis of the signature. Currently, we use the coordinate signature, but later on we will use the polynomial of log signatures. And lastly, we would like to apply more sophisticated machine learning or regression algorithm to our signature-based work, because currently we only use the most simple techniques, the ordinary least square, to do all the regression work. So that's it.
Thanks for Dr. Nihao's excellent talk. So any question? Due to the time limit, we have 2 questions.
you mentioned about the trading period. So how you state the idea how you determine the reasonable value for the trading period or trading intervals, or how small it can be?
It's a good question. Actually, our method is applied to arbitrary trading interval. However, if the interval is small, the regression method would be better. And if we have a longer trading interval, sometimes we need to use a high-level truncated signature to achieve a certain accuracy of the regression.
So let's say if I want to really like implement or build this system, is any basis actually like when the system is actually being executed? Like any idea what's the reasonable value of the trading interval we should to get a good accuracy?
So here we use the tick-by-tick data, and actually I use the tick time about hundreds. So it's in the real-time scale, it's quite small.
All right, thank you.
So another question? No? So thanks, Dr. Inhouse talk again. So